Sorry, couldn't help it. Slaggle's take. Turn the lights on. I'm gonna make. All right. Oh. Hey, welcome back to the Mathnasium. I'm gonna do piecewise functions today. Thanks for joining us. Let's. I say we get started. Do some learning. Bases. It's an illuminated. Okay. Let's jump right in here. All right, so piecewise functions are also known as Frankenstein functions. They've been called that before because it's kind of like taking two separate functions and then stitching them together. It's like they're kind of together in a way, but you're thinking about two separate things attached. And I'm trying to think, a quick example of where you're going to see something like this is through like a cell phone bill. So cell phones, you typically are charged by the minute, or they used to be by the minute. And now it's kind of by data, the amount of data that you use. So typically when you pay for a plan, you'll pay for, let's say, 5 or 6 gigs of data, right? And so you're paying that flat rate for your cell phone bill, and as long as you use underneath that amount of data, you're going to get charged the same every single month. But as soon as you exceed that amount, the bill changes. And in fact, the price that you pay can change dependent upon the amount of data that you use. Ladies and gentlemen, this is a common example of a Frankenstein function. At certain amounts of data, the cost is constant, and at another range or another set of potential amounts of data used during the month, it's not constant. It's dependent upon how much data you used. But like 2 gigs and 3 gigs, you're paying the same amount. It's a constant rate or a constant charge. So there's a quick example of where you will see a piecewise function in the real world. So now what we're going to do is we're going to graph some simple ones. I'm going to kind of blaze through these. You guys can follow along, and hopefully this process makes sense. So I talked about cell phones. Yeah. So here's what they look like. So a piecewise, I'm not going to call them Frankenstein or Frankenstein functions, but a piecewise function looks like something like this. So it'll have like, it looks like this function as long as the x is less, or our x's are less than 0, but it looks like this function in a different range. Now, if you're just plugging in numbers, all you have to do is take the x value. In this case, remember our function is f of x, which means x is -2. We're plugging in -2. We got to figure out which part of the function it belongs to and then evaluate it at that part. Here's the example. For f of -2, since x is -2 and -2 is less than 0, we simply evaluate it at 3 times -2 plus 5. 3 times -2 plus 5. 3 times -2 is -6. -6 plus 5 is equal to 8. However, be careful, because when x is 0, both of these say 0, it actually goes into the bottom one because that's where it's 4x plus 7 if x is greater than or equal to. In this case, it's equal to. So f of 0 is equal to 4 times 0 plus 7, which is 0 plus 7, which is 7. Sieben, Dr. Frankenstein. Okay. In green, take 3. 3 is greater than 0. So we're going to plug it in there. Equals 4 times 3. 4 times 3 plus 7. It's been a long day. Something tells me I'm not going to make it through this video without mistakes. All right. The monster the monster would have made mistakes. At least I could do better than him. All right, let's take a try at graphing this. So what this says, I'm going to do this kind of these four kind of the same way. These next four examples, but what this says is our function is equal to x if x is less than 0, and it's equal to negative x if it's greater than 0. So we have this boundary at 0. So the function changes at x equals 0. So the first thing that I do is I come through with this yellow dashed line. This is my boundary where the function changes. Well, you guys can see. And then that's the boundary where the function changes. And so I'm going to come through and I'll put these in different colors. We're going to think about each function individually. So where is the function f of x equals x? Well, I want you to think about y equals x. Y equals x is a linear function. It's in slope-intercept form, and it's got a slope of 1 and a y-intercept of 0. Slope of 1, y-intercept of 0. So let's go ahead and graph that. I'm just going to use little points. So it crosses right here. And then I go up 1, over 1, up 1, over 1, 1 over 1. So this is positive 1, slope of positive 1. And that's going to go all the way across my graph. I'm just putting these points. This is not my graph. This is like my scratch work, right? Our function f of x equals x or y equals x, our piecewise function only exists at x when x is less than 0. So since it's less than 0, I put an open circle on 0 on my boundary. That's open circle. And then I go this direction to draw my function. Now we've done that side. Now we have to do the right-hand side. On the right-hand side, it looks like negative x. So we have to think about a separate function, y equals negative x. This has slope of negative 1 and a y-intercept of 0. So it still crosses here, except this one is going to be a closed circle because of the equal sign. And then we're going to shade it, or we're going to draw our line on everything to the right. But what does this look like? Well, I didn't really graph it. It crosses here and got a slope of negative 1. So over 1, down 1. Back this way. But we're not interested in these blue points. We're only interested at the x values greater than 0. I always struggle. I gotta graph it in this direction. Using my shoulder. Okay. All right, and that's what our function looks like for greater than 0. So you kind of have to draw two different ones, and you have to see where the break happens. You draw it one on one part of the boundary, one on the other part of the boundary. Pretty fun. All right, let's try another one. Graph the following piecewise function. Start with our boundary. This time our boundary is not at 0. It switches functions at 2. 2 is the boundary. So I'm going to put a vertical line here at 2. Okay, and then I'm going to think about what my two functions look like. In red, I'm going to do the function y equals 4. What does that look like? That looks like it's the line that is all the points with the y value 4. So I just need to find two of those. How about 1, 4 and 2, 4? Hey, look at that. Those 2 points form a line. That line can continue. Okay. So there's my line, but I'm only interested in the ones that are less than or equal to 2. So I'm going to put a closed circle on the boundary and then shade to the left. Shade the x values that are less than 2. That is this direction. Now in blue, okay. In blue, it follows the function y equals negative 4. Those are the points that have the y value negative 4. So 1, negative 4 works. Or how about negative 2, negative 4 works? There's my line. But I'm interested in only the points that are greater than 2. So we have an open circle here. The right. So our function is at 4, 4. It continues at 4, 4, all the way to 2, and then at 2, it's still at 4. But as soon as I get any bigger than 2, just infinitesimally small increase is going to bump me down to -4. It's tiny little small, just, it's like, hold on, let me get in for the close-up. I'm just talking about like, it's going to put me down at -4. Overkill. Overkill. I just ruined my camera. I mean, Mr. Olson's camera. Olson. Yikes. That's awkward. Graph the following piecewise functions and determine the domain and range for each. Oh, goody. Let's add a little step here. Okay, here we go. In yellow, our boundary here is 0. I'm looking here. This tells us our boundary. Colors. Please forgive me. Boundary. That's our boundary. Boom. Coming over here. Red. -x plus 4. -x plus 4. All right, let's do this thing. -x plus 4. What does that look like? That's a line. So in red, y equals -x plus 4 has slope -1, y-intercept of 4. I'm coming up here. I'm going to put my point. And again, it's got a slope of -1. I'm just going to put these dots to show my work. Oh, look at this. All right, so for this one, we're actually interested in the points the left of 0 or less than 0. Right? I'm going to do an open circle going up. Open circle. Following that pattern to the left. Okay, cool. And in blue, we're looking for the line y equals 6. That describes all the points with the y value 6. How about 1, 6, 1, 6, 4? Hey, those form a line. And which ones am I interested in? I'm only interested in the points that have an x value greater than 0. So that is filled in circle here going to the right. Okay, it is in our interest to talk about sometimes these functions don't meet up, right? They don't come to a same spot. There's like a jump, right, between the two functions. But sometimes they do meet up, like in this scenario, okay? So in this one, we almost have like a smooth transition here, okay? In this one, we don't. We have this big jump in y values to go from one to the other. And so that happens sometimes. That's okay. That's normal. That's part of being a piecewise function. You just need to know that at that boundary, the value of my function here is 6, the closed circle. And let's do domain and range. Purple. All right, the domain. When I'm thinking about the domain, I'm really thinking about what are all possible x values? What's the lowest possible x value? Are any x values missing? And in this case, there aren't, right? Every x on this graph there's going to be a point, right? -1, it's right there. 0, it's right there. So there is a value, so we just say -infinity to infinity, or the all real numbers symbol. Excuse my stomach if it's making noises. Shouldn't have had that. 3 bowls of Thai hot curry. Oh, I need to get a sound effects panel for my YouTube videos, I think. All right, and the range, think about the lowest possible y value. Is there a lowest possible y value in this scenario? And yes, there is. The lowest possible y value is 4 up to 4, but not including 4 because 4 is not filled in. That's the lowest possible y value. Highest possible y value. This will continue up forever, so there won't be an upper limit to the range. Fantastic. Next one. Let's do this quick. Pen, red, in x plus 5. That's got a slope of 1 and a y-intercept of 5. So that looks like this. Oh, I forgot my boundary. We'll use slacker. The boundary is not required. It really isn't. It helps me keep track of what I'm doing. I can hardly walk through the grocery store without losing my family. How do they expect me to teach how to math? Let's see. So it is these red dots, but only less than or equal to -2. So closed circle on the boundary going to the left. Blue. Uh-oh. Slope of -2, y-intercept of -1. -1 right here. So there's our slope of -2. Aha! So those meet up. Look at that. Has to go. Now we can connect the dots here. Technically, that's an open circle, but it doesn't matter because they have the same value. Okay, cool. Let's do domain and range. Domain, lowest possible x value. There isn't one. Pardon me. -infinity up to infinity, or all real numbers in blackboard bold. Range, lowest possible y value is -infinity, and the highest possible y value is sweet, and that's included because it's filled in. Yay! And there was much rejoicing. Oh yeah, these are cool. Here are some interesting functions. And when you're talking about paying a cell phone bill, I think this is honestly kind of more how a cell phone bill behaves. You don't pay for like megabytes, and you don't pay for individual megabytes or kilobytes or bytes and then scale those to cents. You purchase, your bill kind of increases in chunks when you're paying for data. And I know I'm about to do a problem that doesn't look like this, but you will have a couple of these that you'll have to transform. So the two interesting functions we're going to talk about is what's called the floor and what's called the ceiling function. So this graph in part A is called the floor function, and this is also a piecewise function that continues kind of forever. It's a repeating pattern where you have an infinite kind of number of steps. They're also called step functions. So it looks like this. So basically how it works is for the floor function, you always round down to the integer, the closest integer less than the number that you're at. So if we're at 0, it stays at 0, right? If we're at 0, it stays at 0. If we're at 0.1, you round down to 0. If you're at 0.5, you round down to 0. If you're at 0.999, you round down to 0. But as soon as you hit 1, you go up to 1, and then you go 1.2, right? If you plug in 1.2, you round down to 1. So basically what this looks like is at 0, it's equal to 0. At and then as you work your way, all of these numbers get rounded, the height gets rounded down to 0. But as soon as you hit 1, an open circle, and you move up to the next step. So this process repeats, right? 1.2 all the way to as soon as you get to right before 2. So 1.9999999. All of those things get rounded down. That's why it's called floor. That's a better name for it. It's sometimes called the greatest integer function, but that's super confusing. So this is called the floor. You just take the number that you're at and you round down to the integer below it. So until you get to the next whole number, and then you round all the decimals after that. So this is what a cell phone bill really looks like in gigabytes, because you're paying for additional gigabytes. And when you use 5.5 gigs, you're still charged for 6. When you use 5.9, you're still charged for 6, right? And then you get to 6, and you hit that, you finish that 5th gigabyte or whatever, and you use any additional data, it typically charges you for the whole gigabyte after that. So there are, why did I sound like I was from Minnesota right there? After that. Where is that coming from? Anyways, this process repeats, and it repeats up your graph forever. Okay, that continues this way. This is called the floor. And as you work down this way, also round down. So rounding with negative numbers is weird. When you are at negative 0.5, you're actually rounding down to -1. So that, just so you know. So when you're at right here, you're rounding down to -1. Okay, so this process continues, and it's just the same pattern. So if you just repeat that pattern down your graph, this is called the floor function. Yay! And the ceiling function would be basically exactly what you're thinking. So this is the ceiling function. And on your assignment, you're going to be transforming the floor function. That's pretty cool. That'll be fun. Okay, here we have the ceiling function. Ceiling function is very similar. Okay, y, which is equal to the ceiling of x. Okay, so just so you know, the floor has the little lines on the bottom. Maybe you guys noticed that. Round down, right? And when I say round, I don't mean like the round you're used to. Like, you just kind of truncate the number and take whatever the leading decimal is really what it means. Take this leading number, and that's what goes there. You take the 1 in the front, that's what, I guess, until you get to the next. But in the positives, it does. So kind of rounding down to that next number, no matter what position you're at. The ceiling rounds up. So if you're at 0, it stays at 0. Oh, hey, that's good. Right? At 0, it stays at 0. If you're at 0.1, so immediately to the right, it rounds up to 1. So it always is rounding up. 0.5 goes to 1. 1 goes to 1. Interesting. So all of these, this is actually an open circle, because anything bigger than 0 is going to get rounded up to 1. And again, this pattern repeats. This is called the ceiling function. Oops. Those are open circles on the left, going to closed circles on the right. That pattern continues. Function. Because today's video is brought to you by water, because that's what keeps me alive. Okay, let's do an actual example. This one is not a step function, but it is a piecewise function. Suppose you have a plan that costs $20 per month for up to 60 minutes talking, and an additional 40 cents per minute after that. Write a function for the monthly cost C as a function of the calling. So really quickly, let's talk about what this looks like. Let's gather round. There we go. Okay, so what's the cost? Our y value is cost. It's determined by the amount of time that we talk. So our phone line is $20 a month, regardless of how many minutes we talk, up to 60. So let's think about this in terms of a table, right? Here's the number of minutes we talk. Here's the cost month. So we can explain it here, right? If I talk for 0 minutes, the line still costs $20. If I could talk for 1 minute, the line costs $20. Now this process repeats, right? If I talk for 60 minutes, this line still costs $20. So what does this look like? This looks like a constant function all the way up 60 minutes. So here we have at 60, it still costs me $20. And this is where it gets interesting. How much does it cost? 1 minutes. At 61 minutes, it's going to cost $20 because it says 60 minutes and an additional 40 cents per minute after that. $20 plus, so as to 61 minutes, plus 0.4, because we talked an additional minute. All right, how about at 62? About 62 minutes. It's going to be $20 plus 0.42, right? Because you're multiplying by the number of minutes after 60 in this case. So this process repeats, and it continues like that. So this is our two functions. So what does that look like? Well, ladies and gentlemen, this is like a line, right? It's going to be start gradually increasing. Your bill for the month, your cost for the month is going to start going up. This is a piecewise function. And so what it's saying is that write a function for the cost c as a function of the calling t minutes. So we're going to say the cost c of t is equal to, hope I have enough room. Hold on. The cost c of t is equal to $20 if t is less than or equal. That looks good. That looks good. So as long as it's less than or equal to 60, we're good. Right? As soon as we start going over that, it's $20 plus, this is if greater than 60. Next limit, $20 plus what? If you don't see, right? You don't see the pattern, do a couple more until you do see the pattern. Take a look. At 63, it's 20 plus 0.4 times 3. So these aren't changing. The 20 is not changing. The 0.4 is not changing. But this is, right? This number, 123, is the number of minutes after 60. So how do we write that mathematically? Well, we say this is plus 0.4, and then whatever is in here, whatever we're multiplying 0.4 by, is the difference between the number of minutes we talked and 60. So you just subtract 60. You can't put just t right there, because otherwise you'd be putting 0.4 times 61, and that's not right. It's got to be t minus 60. You have to put this little minus 60 as a correction factor. And that's pretty tough. Mr. Schlegel made that mistake on the answer key when I was doing that, but it's fixed now when I was first doing it. So it's all right. Just remember, practice this when it's at 61. These are always 60 less, so you have to subtract 60. And there's our function. Okay, now let's actually see a practical application, one that is less contrived. Still a little contrived, but less contrived. Another place that we see piecewise functions is in the calculation of your taxes. A lot of people think that taxes are like, hey, if I make between, let's say I make between $320,000 and $410,000, am I really getting taxed, 32% of my total income? And the answer is you're not. Okay? That's not how it works. How it works is like, it's like a piecewise function with a ton of different pieces as you continue. So if you are married filing jointly, what I am, which is what I do, right? This is kind of what your taxes are going to look like. So I'm going to show you how this works. You want to figure out what you're going to pay in taxes. You look at the different tax brackets and you pay this percent on the, so you always start at the bottom, right? So the first $20,000 of your income pays, you pay 10%. The next 20 to 80 that you make, you pay 12%. Well, let's say a couple filing jointly pays 50. Well, 50 is more than 20. So you're going to pay, this couple is going to pay, let me do here, 10% on the first $20,000. Now, that's a fixed amount for anybody that makes more than $20,000. They're going to pay 10% for the first $20,000 plus, and this is kind of sloppy, plus they're going to do, how much do they have left? 30, but 30 is not going to exceed, you know, the 80 limit there. So they're going to pay 12%, which is 0.12 on the next $30,000. So effectively what I've just done is I've taken the 50, I've broken it up into two chunks, one for 20, one for 30. The first 20 gets taxed at 10%, and the next 30 gets taxed at 12%. Okay. That one should be easy. The first one, 10% of 20 should just be 2,000. Put these ahead of time. Whoa. It'd be $2,000. You'll pay 2,000 on the 20,000. Plus, what is this? Do mental math. Check. 10% would be 3,000 plus 300 doubled. 100. Math teacher. Yeah, hey, I did it. Look at that, folks. I cans maths. So if the amount of that you're going to pay in tax, so the more money you make, right, you're taxed higher in for that money that carries over to the next bracket. The percentage increases. So this is $5,600 is what you're going to pay. Now it mentions in here, it talks about a deduction. So we're going to assume this is after deduction. So when you do your taxes, like this is not how much the family actually brought in. This is the amount that was taxable. That was the amount of taxable income. Okay. Cool beans. Cool beans. Let's roll on to the next one. 200,000. Man, I wish I was this guy. Think about all the beans. Think about all the baked potatoes I could get. I'm going to do this one down here so I have more room. All right, so with this one, $200,000, that's a lot of chunks. You have to think about where you're going to end up. $200,000 is they're going to make it all the way up to the 24% tax bracket here. So that is going to look like paying 10% on the first 20,000, just like the previous person did. But they're going to pay more in the second bracket because they're going to max it out. So on the next 60,000, they're going to pay 12%. So the previous person didn't make it to the cap there, right? They only had 30,000 in this column. So now this person's been taxed on the first 80,000 of their salary. The 120,000 left that needs to be taxed. They're also going to max out the third category, the 22% category. So they're going to pay 22% on the money that carries over into that category, which is 90,000. And I know that because the width of this length, or the width of this tax bracket is $90,000, and theirs exceeds 170. So they're going to pay 10% here, 12% on the next 60, and 22% on the next 90. But then they're going to pay 24%, 0.24 on however much spills into this bracket, which since 200,000, 170 minus 200 minus 170 is 30,000. Okay, so what does that look like? This should be 2,000, same as before. That's going to be 6,000 plus 7,200? Yeah. 7,200 plus 15,000, some amount, 19,800. 19,800. Then this one is going to be 3,000, 6,000, 7,200 again. Okay, cool. Little mental math there. And then we got to add these all up. You can add them all up to see what we get there. These add kind of nicely. 17, 24, 2, 26. I mean, 36 too. Okay, so this is, they're going to get taxed on their $200,000. They're going to pay old Unky Sam 36,200. Exciting. Pretty exciting. That's how taxes work. Yeah. Feeling good. Feeling good. Thanks for watching the video. Let me get up here. Thanks for watching the video. You guys are awesome. You have a marvelous, I got to sit in front of the mic. I hope you have a marvelous weekend. Later.